All right, hello, lovely Year 12s. Today we're going to be starting a new chapter, and we're looking at vector calculus. Okay, and so we're basically combining both vectors, and pretty much our understanding that we're looking at rates of change, but specifically to do with, or generally to do with displacement, velocity, and acceleration. Because we know that if we differentiate displacement, it gives us velocity. If we differentiate it again, we'll get acceleration. And if we integrate, we go backwards. So we go from acceleration to velocity to displacement. So let's have a look at a couple of examples of this. So in our first example here, we've got a particle that moves. So we've got an equation for displacement, and we've got our vector there, and it's asking to find the velocity of the particle when t is equal to 2. Okay, so essentially what I can do is I can write my equation out. So I could even write that initial vector as a column vector. I might even just do that. So just to say, well, our displacement is essentially 2t squared and 2t take 3. So then our velocity in terms of, that doesn't look like a v, I'll try again. Our velocity vector in terms of time is equal to, so 2t squared, the differential of that is 4t. Differentiate 2t take 3 and we get 2. So then the velocity at 2 is just going to equal to 8, 2. Okay, nice and easy for that one there. Find the speed of the particle when t is equal to 2. Well, speed is a scalar amount as opposed to the velocity, which is a vector amount. So speed is equal to the magnitude of the velocity at t is equal to 2. So that's just going to be equal to the square root of 8 squared plus 2 squared, like that there. So that's 64 and 4. And if we chuck it in the calculator, that'll simplify down to root 68. Is that right? Yeah, cool. Which is equal to, I think, 2 root 17. Cool. So that's our speed there. For part C here, the angle that the velocity is making with the positive x direction when t is equal to 2. So we want to know the velocity vector with a positive x direction. So we can draw a diagram if we wanted to. And so our velocity vector goes 8 across 2 up. So we can think 8, 2, and we want to know, well, what is that that angle there? So we can say, well, tan theta is going to be equal to 2/8. So and the angle must be tan inverse of that. We just plug it straight into the calculator. That'll give you 14.04 degrees, like so. And for part, so let's put these here. This was part A, that was part B, and this was part C there. For part D, the acceleration when t is equal to 2. So for that there, we're just going to differentiate velocity again. So our acceleration vector is equal to, and in terms of t, so it's just going to be 4 and 0. So which just means it's constant, so it doesn't actually change regardless of time. So so it's just going to be at time is equal to 2. It's just going to be 4, 0. So it's only accelerating in a horizontal direction. Okay. So I should have just indicated here as well that our velocity vector is equal to d dt of r, and our acceleration vector is equal to the derivative of our velocity vector, like so. All right. So So that involved differentiation. Now we're going to have a look at integration, okay, and how we can use that. So we've got a particle's initially at rest with a position vector, and t seconds later, its acceleration is given by that amount there. So we're given an acceleration vector and an initial position, but not a position vector, not a rule to determine its position at any point. So let's write down our, so we want an expression for its velocity. So essentially we've got a vector there, which is just going to be 8 cos 2t, and just 2 for that one there. And so really our velocity vector is just the integral of a dt. So that's just going to be equal to 2, if we integrate that there, so that's going to be 4 sine 2t. Let me check if I differentiate that. Yep, and that's going to be 2t for that particular value there. And then we've got plus some constant amount here, okay? Now, it says here a particle is initially at rest. Initially at rest. It means that if that's the case, then velocity at time is equal to 0 is just going to be 0, 0. So that means if I sub in, so that means v of 0 should equal to 0. And if we do that, sine of 0, 0, 2 lots of 0, 0, yep, so therefore c is going to be equal to 0 in this case here. So that means our velocity vector is going to equal to 4 sine 2t and 2t there, okay? Don't forget the plus c. Cool. Now we're going to have a look at the next one here. So the value of t when the particle is first traveling parallel to the y-axis. Okay, so let's think about what's happening here. So I'm going to do, all right, so part B, the value of t when the particle is first traveling parallel to the y-axis. So if it's traveling parallel to the y-axis, then we're just thinking about its velocity vector, and the horizontal component should be, we're only looking at just the x direction, okay? And it's when the y component must be, or the I component must be equal to 0. So if I draw a little diagram here, and we want to know where is it traveling parallel to the y-axis. So where is our graph going, traveling in that direction there? So that's when the I component 0 and the y component is something. So we want to find when 4 sine 2t is equal to 0. Okay, so that means when sine 2t is equal to 0, so that's when 2t is equal to, so what values of sine gives us 0? Well, sine of 0 is equal to 0, so we get 0 pi 2 pi blah 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 blah. So that means t is equal to 0 pi on 2 pi. So essentially every pi on 2 degrees. And so here it's asking us the value of t when the particle is first traveling parallel. So, well, it's initially it is. So the answer for that there would be, so t has to be greater than 0. So therefore t must be equal to pi on 2 in that instance there. All right, and part C of this one here, we're asked to find an expression for the position vector of the particle. So again, our relative position at any particular time is equal to the integral of the velocity vector dt. So let's go integrate our vector. So what are we going to get? Integrate sign becomes negative cos. That's going to be negative 2 cos 2t, and we're going to get t squared, and that's going to be plus c. Okay. Now we want to know. So that's our vector there. Now we know from the initial bit that originally it has a position 2j. So it's got a position 0, 2. All right, so that means if I put in t is equal to 0 into these ones here, that's going to give me a minus 2. And all right, so let's see what we've got here. So we know that when I put in 0, I'm going to get 0, 2 is equal to, if we put in 0, I'm going to get minus 2, 0 plus c. So therefore, c must be equal to 2 and 2. So therefore, if t is equal to 2 take 2 cos 2t and t squared plus 2, like that there. Okay, and I can just write it like a column vector. Alrighty, so there's an example where we're doing differentiation integration. Just want to show you one last thing as well. I want you to think about what the following means. So I'm just going to find where these examples were. All right, this relates to integration. So what happens if I said I wanted to do the integral between, say, 2 and 0 of the velocity like that? What happens if I did okay, 3 different equations, and so one without the absolute, one with the absolute value of all of it, and one where we do the absolute value of the velocity and then we integrate it. Well, initially we said, well, this is when we come back to the top up here, we said when we just do a basic integration from velocity, it will just give us the displacement. So this is just going to be, well, this is just the displacement. Or displacement t is equal to 2. Okay, and then so after we've done that there, if we were to do the absolute value of that there, that would give us a magnitude of the displacement. Okay, and that's all it is. So the displacement can be, it's a vector, so it could be both positive or negative. And so this, in the second one here, we're just figuring out the magnitude of the displacement from t is equal to 0 to t is equal to 2. Okay, and so if the displacement was negative, it would just make it a positive value. So then our third one here, what we're going to be doing is we're thinking, well, we're looking at the absolute value of that there, and then we're going to integrate it between that value there. And this in fact tells you the distance from t is equal to 2. Okay, so the main ones you're going to be dealing with will typically be this one here and this third one here. So if you want to find a distance traveled, so if you want to find a scalar amount, you do the absolute value of that one there and integrate it. Otherwise, if you just do a plain integration, that'll tell you the displacement there. So just one thing for you guys to consider. All right, thanks guys. That was chapter 7a.